So, thanks for the introduction. As mentioned, it is towards a reliable software infrastructure for knowledge-driven robots in agriculture. Our motivation for this work, I want to show on this graph. So when we make a graph with the task complexity and the autonomy, we have some specialized robots right now which can do simple tasks, very autonomous, like a vacuum cleaner that does just really one task, but not really some complex decisions. And on the other hand, we have some conventional machines that are operated by the farmers and where the farmers do all the decisions. And where we want to go is in the upper right corner, where we can really do some complex tasks fully autonomously. So for this, we want to get a long-term autonomous agricultural robot for complex tasks. So from the long-term autonomy, there is a demand for high reliability and robustness. And from the complex task, we have a demand for the intelligence. From this, there comes some symbiosis and also a tension field. So when we become more intelligent, we can become more robust. But when we, for example, use a neural network, it can happen that we become less robust. So with this, we have to deal also. Because of this, I will shortly show our robotic system we are working with. And then I will talk about the intelligence, the robustness, the tension field between it, and I will finish with a summary and our remaining open questions about which we can also talk afterwards. So the first system we use is the ARC system. It is an evaluation platform, and the ARC stands for Autonomous Robust Outdoor Exploration Platform. It is a multi-purpose robot with some flexible sensor and actor setup. This is how we use it normally with some Regal scanner on top and hyperspectral camera. So this is the one for the outdoor work and for the agriculture, but we also do have this MobiPic with its a Mir 100 mobile-based platform with a universal robot 6 degrees of freedom arms on top of it with some camera and a robotic 2-finger gripper. So this one is used in projects towards a human-robot collaboration. So all our ideas are not just for the agriculture, but we want to apply them also in some industrial settings. So with the intelligence, I will start right now. Our current state is that we do have a combined semantic and geometric environment representation, where we represent the geometry as 2D geometries, and we annotate these with RDF triples to get some semantic information into the environment representation. In the environment representation, there's also a forward reasoner, so that we can infer everything that can be inferred. So it is rule-based that can be extended with some custom rules, and it implements a Reti pattern matching algorithm, if somebody knows. It is incremental and decremental updatable, and it tracks its own path of the decisions, so it can explain its results. Additionally, we have some processing modules which infer further information from the geometric information. So a really basic example is when we know the position of the robot and the geometry and the position of a field, we know if the robot is on the field. Additionally, this environment representation is also connected to a hierarchical planner. So the planner queries some symbolic information from the semantic environment representation so that it can create the plan. And while execution, the execution layer can query the information for the concrete metrics from the environment representation to translate the symbolic plan to actual positions. Where we want to go with this is that we get a closer integration of the reasoner into the overall system. So, for example, that we can infer the geometric information directly into the reasoner, so that we can infer, for example, a waypoint where we have to drive first before we can grasp something on a on a geometrical level, and that we can also trigger actively other components. So when the environment representation gets the information that there are, for example, some bad weather forecast, that the robot should find some protection against it. Additionally, we want to devise a generic strategy to handle this translation between the symbolic and the subsymbolic layer, so that we have a generic way and that we enable the robot through this for a knowledge-driven behavior. This was about the intelligence, so I want to start with, continue with the robustness part. There I want to start with how our system, when we normally have the robot, there we have the hardware and drives, the machine files, all the libraries, all our nodes, so mainly our code, and the ROS core, which is connected to everything. So when we want to do some snapshot or some rollbacks or just some easy deployment, we do have the problem when we do some development on the demonstrators and we want to do a rollback. This is quite easy with our code because of the Git repositories. But if we want to do a rollback on the libraries, we might have some troubles to install everything again. So our idea is to use the well-known Linux containers from the cloud computing and to translate this to the robot itself. So when we put it into a container, we can just make a snapshot of this container and you do some rollbacks to go back to a working snapshot or to deploy it easily on a new robot or even to get it to a new developer easily in a working way. This is just the first step because we can go even further from the cloud computing. We can use multiple containers so that we can split it up. For example, when we just take the web interface and put it in an extra container, we can maintain or do some development on this part separately, and we can also do the management and monitoring independently. So when the GUI crashes, we can restart it independently from the rest of the robot system. From this, there's then easily one step further to just put everything, to use also a remote machine, because already beforehand the robot doesn't even know where the containers are, because everything goes over the TCP connection of the ROS core. So when we want to use a new feature like a new neural network which needs some more computing power, which we do not have on the robot, we can just add a remote server and put the container onto the server so we can easily update and even upgrade the robot, even though we don't want to touch this long-term autonomous robot. So these are our ideas for the deployment and the service, but there are, for the robustness, always some ideas about the safety and issues where there are some quite obvious goals for autonomous robots which should not do any harm to humans, animals, environment, or even to itself. So we are not interested in avoiding this especially. We have to do it to destroy nothing, but our main focus is on the planning behind it. So how do we handle this safety intervenience? When we just take a look at this, there are for the human, there are the harm of collisions, or that we manure somewhere is a harm for the environment. And the bad weather could be a harm to the robot itself. So these are on quite different levels when we want to take a look at it. So just a collision is a direct sensor input. We don't want to drive into the wall. And the bad weather, that is more high level because we need to first get the weather forecast. We have to check how long do we need to get back to our base station. So if we take a look at this basic boxes and arrows on the architecture from the robot, we have this sub-symbolic level from the world, the sensor, the controller, the actuator in the loop, and the symbolic decision making on top of it. So when we just draw some arrows in there, the first level is just the current control, for example, for the actuator, that we don't destroy the motor. And we have the collision avoidance, for example, where we get the sensor input and give it back to the controller. Or we do some more high-level decision-making, like avoiding the bad weather. Our idea behind these is that we use this in the tension field. So this is the whole architecture, more or less, for the robot, which is a lot at the first sign. But our idea is that we model the safety parameters explicitly in the environment representation, so that we can regard the safety first in the planning step, and that we also, when we have some safety intervenient, that we give it back to the knowledge representation and save it there explicitly as, for example, there is a wall or we do get bad weather, and then we can do the task planning again on the symbolic level to regard the intervenience we didn't foresee in the first step. So overall, we do have a semantic and geometric environment representation where we want to do further work into the semantic and geometric information. We started with a containerization in our robot, and we are thinking of how far we can go and which advantages we can take from the cloud computing. And we have some concept for the feedback of the safety intervenience in the planning. But there we don't have the concrete ideas on how to handle the symbolic replanning. So, thank you.
Thank you very much. I have an announcement to achieve before having some questions. There is a BMV, a black BMV, the immatriculation plate. It's CY 289TJ, which is not well parked. So if somebody has a BMV, a black BMV, he has to remove his car. Okay, it's not in this room. Perfect. So do we have a question? Sorry, don't be shy. Yes?
So when you're talking about robustness of the system, is it only based in software that like you split it up in Docker containers and all that stuff? Or do you also think about hardware, reliability, redundancy of systems and all that stuff?
Yeah, it is mainly the software part.
So you're using there, I saw a lot of ROS. Is it like ROS 2 already, or is it based on ROS or on any real-time version?
No, it's up to now it's still ROS 1 because, as you know, there are not all capabilities in ROS 2. And yeah, we are more on the development side, and we don't, well, we care about real-time, but it works for our purposes.
Any other question? Yes, please.
In the containerization, which software have you tested?
Right now, we just use Docker.
Docker.
Yeah.
Last question. No question? Just a small one. When you detect a fault, what do you do after? You just stop the robot, or you have some new behaviors to put the robot in safety?
You mean which? No, I didn't get it.
When you have seen a map, a graph with I can detect a fault there, and there in red marks.
Yeah.
So what did you do when a fault is detected? You just stop the robot, or you have another safety behaviors?
Yeah, that depends on the error. So when the fault is that there is a wall we didn't expect, we just do some replanning to avoid the wall. So when the battery is unexpected low, we do some replanning to get back to the base station. But when the error is that the motor is broken, then we have to stop.